First, this is my normal voice, so don't feel bad. I wanted to talk to you about a friend of mine. Her name is Sarah. She's 34 years old. She's great. She's incredibly funny. She's full of energy. She's super smart. And about, I think, early October, we were coming back from the gym, and she felt something weird on her left breast. She got it checked the next day at like a local doctor, who also found that the mass looked pretty weird. And so he sent her in for a mammogram. The mammogram looked bad as well. And so she was sent to another institution for a biopsy. Basically, it's a surgical practice where they pick up a small tissue part to get it analyzed. The biopsy confirmed that she had cancer, but she didn't know which type and which grade and which stage. After that, she had to do an MRI. The MRI is a radiology examination where you kind of define the grade and the texture of the mass. And that confirmed a grade. After that, she had to do a genetic test to see if the cancer was genetically related to her family or if it was environmental. Guess how long it took to do all these examinations in New York City, which is one of the most advanced places where you can be treated with cancer. And yes, it got 6 weeks. You're close. She was diagnosed with triple-negative breast cancer, which is one of the most aggressive breast cancer you can get. And so she had to get treatment straight away. To get that diagnosis done in 6 weeks, she was actually running around with a CD of her digitized pathology images that she got in one institution to another institution. Why? Because the labs were in one place, the oncologist and the surgeon in another place, the key opinion leader in breast cancer, which was basically the second opinion, in a third institution, and nothing was shared. So she was literally diagnosed with breast cancer, running around in New York City with a CD of her data. That's insane. And so why am I talking about this? It's because for cancer diagnosed, you have to bridge data silos. You cannot have a cancer diagnosed without considering pathology, which is the tissue, the biopsies, radiology, genetic data as well. And the other silo, which is insane as well, it's the institutional one. Apparently we have E.H.Rs, which are electronic health records, which could be very easily shared, but they're not. Why? Because they're there, but institutions don't have agreements between each other to share that data. And so what happened to Sarah? Sarah started the standard of care treatment, which is a double cycle of chemotherapy, ahead of her surgery. Why ahead? It's just in aggressive cancers like triple-negative breast cancer, you have to go through some type of treatment before surgery to ensure that if there are any lonely cells traveling around your body, that you kill them. So the assumption is if the mass, the node, is shrinking or it's changing texture, then all the lonely cells will be affected by the treatment as well. So she gets into 3 months of treatment, 6 weeks and 6 weeks. Then she gets to the surgery. The surgeon removes the mass, and the mass gets sent out again for pathology to just check if there are any more cancer cells. 3 weeks later, results come back. This is over, now it's been pretty much like 4 months, 5 months. This is insane that it's been that long. And great news, she has a complete response. That's incredible. The chance of her having that are like below 5%. As a general knowledge, half of the people that get diagnosed with cancer die. This is just a, and in triple-negative breast cancer, the stats are way higher than that. And so, why am I telling you this? It's because she was incredibly lucky. There is nothing I mean, there is mentality and there is optimism and be a fighter, but at the end of the day, it's a very aggressive disease. And so what if the treatment didn't work? Then she would have had to go through a second line of treatment, which would probably have been chemotherapy again, just a different regime. And then if that wouldn't have worked, she would have moved into targeted therapies. So the targeted therapies are immunotherapy or other type of direct pathway, which means that the chemotherapy doesn't target one specific organ in your body. It targets everything. So it kills cells when they're reproducing. And why do they do that? Because cancer cells reproduce very fast, so it's a way to actually avoid the cancer from spreading. Targeted therapies are very different. Targeted therapies work when you have specific receptors on specific cells. But that's why you do the testing. And that might have not worked, and then she would have moved into something even more exploratory. What if you could have predicted Sarah's response to a specific treatment in advance? That's kind of what we do. So what we're doing at Owkin is to first bridge the data silo and use multimodal data integration. So for a patient like Sarah, who was enrolled in several clinical trials, we would have digged all her information and combined it together. So it wouldn't have been only the clinical information from one institution, the pathology from another, but we would have had Sarah with all the data available on Sarah, from pathology to radiology, omics data, and clinical data. Then we are federating a network of institutions. What does that mean? Federated learning means that we are connecting institutions together through nodes, which is just a technological infrastructure that enables models and AI technologies to be trained remotely across a network of partners without having them sharing the data between each other, because they don't do it anyway. So that's a way to solve the fact that histology is in one place, radiology is in another one, and the clinical data in another place. And what are we trying to do with all this data and this federated data is to predict disease evolution, patient response to a treatment, and toxicity. And so for the case of Sarah, we would have been able to say that actually the chemotherapy would have worked on someone like her. And on another patient, we would have been able to say that the chemotherapy wouldn't have worked. And so then, instead of wasting 6 months into 4 months into one specific treatment, you move straight forward through the value chain. And for aggressive cancers, for all cancers, but specifically for aggressive cancers, like triple-negative breast cancer, she was diagnosed with stage 3. There are 4 stages in cancer, so it's pretty much as bad as you can get before there is no more treatment for you. Doing that and being able to predict if a triple-negative stage 3 cancer patient will not respond to chemotherapy is huge. Because then you save 5 months, you move into a different treatment, and the cancer doesn't spread during those 5 months. Because if it's not responding, it's usually either stable, but usually not in such aggressive cancers, and usually it's spreading around. And that's even worse, because when you have metastasis to the cancer spreading to other organs, it becomes even more difficult to treat. So that's kind of the challenge that we have for ourselves. We're building this network in Europe, in the US. We're going to be looking at Asia as well. Why is it important to have a network that is not a local one? It's because the heterogeneity in data. Every patient is different. And to understand and to really make medical discoveries, you have to take into account this heterogeneity. It comes from a genetic background, it comes from an environmental background as well. And so that's why it's very important to have institutions across the world. And once again, I cannot emphasize enough how important it is to have the multimodal approach in cancer research. Once we have those predictive models, by the way, they're not that easy to make, but once you have them, how do we use them to change actually how Sarah is going to be treated? it goes through a chain. So the first way, it all starts with research, which is 100% what we do. And then it moves in drug development. And that's what, I think the easiest way to think about drug development is through clinical trials. So the way we apply those models to clinical trials is to identify subgroups of patients that will respond or not to specific therapies. And that enables us to shorten the length of clinical trial and really identify the subgroup of patients that will benefit or not from a specific drug. And the next phase is that the drug gets approved and delivered to the specific patients faster. And so the clinical impact is that patients with triple-negative breast cancer that are going to be diagnosed in the next month and years will have access to a targeted treatment, a precise treatment, ahead with drugs that either are already on the market or are not yet on the market. And so to conclude, there is a big race between data and knowledge in medicine, and specifically in oncology. And what we want to make sure is that through machine learning, predictive models, and through a federated network of research partners, we make knowledge wins versus just data. I'm done. I can take any questions you might have.
Does your company, first of all, thanks for being here. It's really great what you're doing. Does your company have any hope for a long-term being able to either almost identify people who might even be at risk for cancer? So like obviously the first step is getting quicker to the diagnosis, figuring out what treatment might be effective. But do you guys have long-term plans of trying to figure out like what are key identifiers that these people have that maybe would be able, would mean they were predisposed?
So it's a very good question. So when you analyze data, which is from observational studies, so real world data, and from clinical trial, what we look for are biomarkers. Biomarkers are things that indicate that you're going to be a responder or not responder to specific things. If we make a discovery on one of them that actually is biologically meaningful, because that's exactly what we look for, the models that we build are not like black boxes model, they are interpretable. If there is a biological reason, there might be the next thing, which is like a genetic criteria or an environmental one. When we make that discovery, this is actionable in epidemiology, so prevention, and in clinical practice as well. So yes, so it's exactly the same discovery. It's nothing different. It's just how you implement it. If it's something that is genetically related, then it should be scanned for. And so this goes into prevention. And if it's something that can be impacted through a specific drug, then it's more on the clinical use case. So it's exactly the same technology, can be applied to both. Ourselves, we don't do the diagnostic part, but that's done with we partner with research institutions and their KOLs, and they're the one that do the diagnosis. But the discovery that we make are obviously applied to both. Yep.
How do you connect to patients?
We don't connect to patients directly. So we work, as I was saying, so it's us, and then there is the oncologist, or the professor, or the surgeon, or the pathologist, or the radiologist. We work with them. We don't work directly with the patient.
And like how many institutions then, like care institutions, are you connected with at this point?
I think we are like in the 50s. It's a big network for cancer research, and it's growing every day. We also work with the usual way of doing this, it's through consortia. So the way that research institutions work together on specific research projects is usually by creating a consortium where data is pulled together and analyzed for a research purpose. What we do is they don't have to create those consortium because the data stays in the individual centers, but they collaborate through research. Yes?
Are you getting to the diagnostic phase? Like, would you have to go through FDA approval or anything like that? Because I think there's a few companies that are having issues because the standards have been...
So it's a really good question. So no, we're not into the diagnosed. We're really 100% on medical research. So we are very lucky because we have investors, so we are backed as a company. And so it's great to work for a company that doesn't have a revenue target. So that's incredible. And because the value of what we do is really a medical discovery, and which will be monetized through drug development in the future. But we're not going ourselves into the diagnose. Obviously, some of the algorithm that we build can be used for diagnose. We are exploring ways to partner with specific companies to maybe get those down the diagnose line. But we're not going to go for it ourselves. It's not only, so I'm going to take you, it's not just regulation. The other big thing is distribution of your product, because there are different circles. Everything that we do with partners, academic partners, is free of charges. So we don't pay, they don't have to pay us for anything. We share revenues if there is a medical discovery, which we will be able to apply to the drug development. Then we share the revenues with our partners. So if you move into diagnosis, it's a different path. Yep.
Hi, thank you for being here. I was just wondering, there's many types of cancer. How do you decide which area to focus on?
Yeah, that's a very good question. At the so we have been around for 2 years, just for you to know. Very early days, it was kind of more opportunistic. So we had network of researchers that we knew, and so we started working with them. Now it's more driven around two things. So the unmet medical needs, so big pockets where there is no specific treatment, or where the heterogeneity in response is way and non-understood. And the other thing is pharmaceutical interest from the drug development. So we kind of match those two.
You mentioned about the discovery. My question would be, do you develop a intuition at the get-go in terms of how long it's going to take and how long you're going to give in the time for?
Sorry, I didn't get. What
discovery, in terms of, do you have an intuition on how much time you would put into it?
To make a discovery?
Yes.
So it's what we do every day. So it's let's say that you have a standard project. There is one KOL. KOL means key opinion leader. So he or she has great knowledge on one specific disease area. She has access to she has curated a cohort of patients for the last X number of years. There are pretty much, I don't know, like let's say 200 patients, 300 patients. Then we have automated everything that is pre-processing of data, so that goes very fast. And then there is the machine learning algorithm that we build on top, and the interpretation of the results. That's when we work again with the KOL to really understand the biology behind the results. And this can take, the longest part is to, if we don't have an agreement in place with the institution, is to get that done. That can take up to like 6 months or a year. If the agreement is already in place, then it can go very fast, and then it's a couple of months. But it depends.
Yeah.
Yeah.
So you talked about creating predictive analysis models in the institution because they're not sharing data with each other. So I feel like if you collect all the data that's being generated all over the world, you get a much more valuable data set, which can lead to identification of patterns, which might not be possible in silos. So what is the reason behind them not sharing data? Is it like professional rivalry? Is it like bureaucracy? Is it regulation?
So it's a good question. It's a lot of different things. So there is a regulation which are very different by country in terms of patient privacy and medical data security. So that's one issue. There is also the issue of where you have to store the data. Can you store it on the cloud or on premises? In Europe, the regulation is different from the US. And then there is just the competition in the medical research field, where It's competition to get published, it's competition to get grants, it's competition to maybe get like contracts with the pharmaceutical industry to exploit your discoveries. It's a lot of different ways. What we propose is the data stays in-house, which can be in the cloud or on premises. We're agnostic. And the models are trained across the different data set, but the data is never shared. And so it's kind of, institution 1 will benefit from the data set of institution 2 without never having to see the data set by itself. It's just that the model will be stronger because it would have been trained, as you said, on heterogeneous data and larger data set as well.
Thank you.
Yep.
Hi. I'm wondering how you guys are handling the problem of health data being inaccurate. So hospitals have a problem where sometimes the data is just entered wrong.
Yeah, so that's a good question. So that's exactly what I was trying to emphasize with the multimodal data approach. Because the data can be wrong at a clinical level, but the data is rarely wrong at a pathology slide level. So if the only thing that could be wrong is that it's not the correct slide for the patient, but that doesn't happen. What can happen is that the data is not entered correctly and all that stuff. That's why we say that going back to the raw data, which can be pathology, radiology, or genomic, it's crucial. That data, what it's used today, it's mostly the clinical data, which is the summary of the findings on the other type of data. What we say is we're going to use it, but we're going to use everything else, because everything else has way more value than what it's today actioned for.
We have time for one more question. Is there any?
Yep.
So how do you take care of accuracy and security? Because if you predict something, so that has to be how much % your accuracy, like if you have done for the past 2 years, how much accurate you find the results?
Oh, we are accuracy will be on the 97 and above. So it's high. It's matching or higher what a pathologist, what a physician will guess.
But then how will you prove the accuracy? Like in what standards or grounds will you compare and prove the accuracy?
So when you have a data set, you will divide it into a training set and a validation set. And then you validate on other data sets which are don't have the same format because they're from different institutions and from different type of patient population as well. So you kind of validate within the same data set and then on other data set as well.
Okay, that's all.
Thanks.